So I have to sit on the other side.
Perhaps.
Okay, it may not hold. It's fine.
Is your cable long enough to reach that height? No.
No,
Okay.
it's okay.
Okay, we'll find it. Maybe you can reduce your brightness a little bit. Hope for the best.
Oh, that is also my daughter. Bluetooth. I don't need Bluetooth, right?
No, I don't think so. Okay. Oh, I see. This is a notification here. You will keep the chat. I can let you know if something.
Okay.
comes up.
Yeah, I mean, you can keep it open, but I won't see it, right? Because I'll be looking.
You'll be looking there, so that's fine. Yeah, it's okay. I'll have it open. Okay. So, are you good to go?
Yeah.
Hi, awesome. Hi, thanks for joining us. Welcome back to the seminar. We have our very own Balagopal telling us about how language influences its use, or something like that. You're going to say it better anyway, so it's
Yeah.
okay.
Okay. Okay, I thought there would be no introduction. Should I thank? No, I think I am kind of co-host, right? So,
Yeah, that's right. So I don't know. Right. So maybe I could have, okay, you shared a bio with me, which I should probably read out. Would you like me to?
no, it's
Okay.
fine.
All right. So, yeah,
I think this is just
introduction.
this is mostly my complexity class.
We saw linguistic relativity and we
Oh, okay.
have a project on that. But we can't hear what it's about.
Okay. Oh, but I am not going to be talking about theory of natural languages.
That's why I'm sitting here.
Okay, sure. Okay. So, hi. Am I audible to the online audience?
Yes, sir.
Okay, thanks. Right. So, I want to do like a pair programming session. So, I will write the same program in two different languages. And what we do is we will see how you are thinking about the problem. Right? So, in the theory of natural languages, there are these theories called linguistic determinism, linguistic relativism, and universality of languages. Right. So, if I make any mistake here, you can correct me. So, linguistic determinism says that the language structures, right, that determines how we think about stuff. Right. So if something is not in the language, then the strong hypothesis to make is that okay, we cannot think about it, or that is why it's called determinism. So there is a weak or a weaker version of this theory, which is linguistic relativism, which says that it does not determine, but it still influences, right? And I think determinism has been discredited by now, kind of, at least. It's kind of hard to believe that if you speak a different language, then you wouldn't be able to have the same thoughts as me. But linguistic relativism, I think, has some positive evidence, right? Especially related to, I think, things like colors, where if your language has a name for a color, let's say English has a name for purple, then you are able to let's say think about that color in a better way. Like whatever you think of as purple is actually purple. Whereas if your language does not have a specific name, it's kind of hard to retain that concept of this particular color. Right? So these are like, I think, brother theories. So the opposite is language universalism, universality, which says that thought is completely independent of the language. So it does not really matter if I think about a banana. I don't need to know the word banana, or it has zero influence. So language is purely a means of communicating thoughts and not actually something that I use to have thoughts. So,
So sorry, I know nothing about linguistic theories, but are there theories which account for like a classification of thoughts? Like certain kinds of thoughts don't require language, certain kinds of thoughts do.
okay, yeah, this is a good question. I cannot answer this maybe.
So it's much easier to think in terms of color. Like you said, there was a famous study with the Russian blue, where the Russians have a color for light blue. So they're able to, it's very hard to check if you have seen the blue, but they're able to discriminate between different shades of blue better. The Russians who speak that language than they also did it with Greek immigrants. When they learned the new language, they also gained this perception. So your perceptual ability is somewhat influenced by language, which is sort of a higher level. So we used to believe in something called cognitive impenetrability, that these are things that will work everywhere all the time. But now it seems to be penetrating with culture and languages. So there are many other examples. Say, for example, even body parts and division between body parts. Different. I think Croatian has a word for the division between the wrist and the hand, so they're able to identify it faster and things. So it's like a lot of studies in that direction. The colors well studied, they also found that your organization or the way your visual cortex or the part of the brain that processes color changes because you have this.
Oh, wow.
So the color, it's sort of well studied. We are trying to study it with some practice. But of course, for objects and things like that, you can see an object, interact with it, but you don't need a language for it. So, so it depends on how we define thought, how we define, whether you're discriminating, categorizing, naming, interacting.
Color does seem like a semi-concrete, semi-abstract concept. Somewhere between say, feelings and emotions are very completely abstract.
I think feelings and emotions very clearly language does affect, because a lot of if you look at the history of emotions, the words that we use now, like depression, sad, they have to be invented, and sometimes they were not there. So there, when you name things and you define and culturally, then you tend to have these emotions. So we are not, at least I am not interested in those things. That clearly culture can influence this kind of stuff. But talking about really basic perception, because
Just to clarify, the theory is not saying that you can't be depressed because the language doesn't have the word.
no, I'm saying as a
Yeah,
gross
you can
example.
express it, yeah.
But there are certain emotions, like I think the Burmese have something like, you find this in the internet also, like the feeling of when a friend goes away, which fills up the room, and things like that. They have a specific word for that, and we don't. And you find this in the Insta and the Facebook very well. So those are, if you have the words in the literature around it, you tend to report having those feelings.
Okay, right. So we are going to look at it only from the programming languages perspective, which is easier, right? Because programming languages are very structured. So you know exactly what the valid programs are and what are not. So if it's accepted by the compiler, it's valid. But English, or I think any natural language, does not have some such very precise binary classification. And programming languages solve very specific problems, exactly the decidable computational problems, some forms of infinite time computation. So so this is what I hope to like experiment on. So this is not really a comparison of languages. I'm not saying that one language is better than the other. I mean, I do say this, but not in this lecture. In this lecture, I'm just going to compare. So you might have also heard, or I have heard many people describing this fact that programming languages have personalities. Have you heard of this? People doing this, right? So I think at least one or two people have. So I think what it is because we have different ways of thinking about solving problems, right? So some of us like to work with a lot of examples and build theorems from there. And some of us like to get the high level picture of the proof and then, so basically a bottom up, top down approach. There are different kinds of people who are comfortable with the different kinds of thinking. And I think this is what people mean by personality. So whatever their thinking style, the languages that encourage such thinking patterns are probably a better fit for them. So I think this is the fundamental reason for people thinking that languages have personalities. So we will look at two languages, Python, which I choose because it's extremely popular, or you know this, OCaml, which is not popular at all. But you will learn some part of OCaml, I think. Or at least I believe it is intuitive if you have seen some mathematics. Okay,
Would it be
cool.
fair to say that OCaml is increasingly popular in certain circles?
No, not really,
Right.
sadly. Okay, so I have to choose a problem to compare. So it has to be easy enough so that we can do it in 1 hour or half an hour per programming language. And I don't want to spend too much time describing the problem because it is completely uninteresting. And this phenomenon uh, repeats for many programs. So you can test this out. So my problem is to represent natural numbers. Python already does this. So it has true natural numbers in its data type set. Uh, so let me illustrate. So we start Python and I can do things like this, right? I can take any natural number and multiply them. Uh, but this is not a true machine operation, right? Because machines have bounded integers. I think they support only up to like 9 digits. Anything above it is a more complicated operation. Right? So what we are going to do is we are going to implement or re-implement natural numbers in the case of Python. Right? So assuming that Python only gives us 2 digit integers, how would you implement arbitrary n-digit integers? Right? This is true for C, but I don't want to program C. Uh, and the representation has to be reasonable, which means n has to be n should take only log n storage, and we are going to implement n plus m, which should take linear time, right? So any natural number representation that does not satisfy this property is completely stupid. Uh, right? So your place value representation or whatever, it satisfies these two conditions, right? Uh, so if you take something like Roman numerals, they don't. So this is why we don't use Roman numerals. Uh, they are an additive system. So the representation takes n storage for the number n. I think Roman numerals only go up to 1,000. After that, you just have to repeat. So if you have to write 100,000, you have to write 100 n's.
You say it's linear and
Yes,
mathematical.
yes, it is linear because it's an additive system, whereas the place value system increases the power, right? So, okay. Right. So let's assume Python will only give us 2 digit numbers. Now, how would you represent unbounded natural numbers in Python? Okay, pair programming start. Give me a representation.
I don't know, list or something.
Right. So a list of digits. So let's see. Okay, so let's say I want to represent 1, 2, 3, 4, which is clearly not a two-digit number. So how would I represent this, Anirban?
So 3, 4 or 3, 4 in the first element of the list and 1, 2 in the second element of the list.
Okay, that's a good choice. I will only keep single digit per position, but he made an interesting choice here. So the lower order terms came first. Why? Okay, everybody is regretting coming to this.
Whenever you choose the first element, it's popping out, so it becomes the 4 is the ones position, becomes 3.
Right. So what is the advantage of putting the ones position first? Let's look at our problem. Oh no, don't answer. Okay. Right. So the head of the department knows the answer. It is that we are performing addition, right? And the natural way to do this is start from the units place and proceed towards the higher order digits. So this representation makes sense because we can walk down the list and add stuff. Okay, so this is the representation that we use. And why don't we use two digits? So why didn't we take 34, 12?
Maybe because you want a multiplication and when you multiply multiple two-digit numbers, then you have a digit more than 2.
Okay, close enough. So if you add two two-digit numbers, you do not necessarily get a two-digit number. But I only have two-digit numbers. So I want to perform addition without overflow. This is a common technique if you have a 64-bit machine. The large numbers are sometimes implemented using 61-bit addition. Sorry, 63-bit addition, where the 1 bit is retained for overflow. But I'm not going to like pack a lot of performance into this. Nobody should use this for any real application. So a single digit helps because addition, whatever number I get after adding two digits is still representable in our imaginary system. Okay, so
You still have to worry about carries.
yes, I still have to worry about carries. The point is that the carries are now representable in my system. Yes. So if I do 9 plus 9, I get 18, which I am allowed to use because it's a two-digit number.
But
Then
but you're breaking your convention of using single digits, right? I mean, if you have a sequence of things you want to add.
no, I'm not going to break the convention of having only single digits in the list. Right? So I have two things here. So I have lists and I have two-digit numbers, and I'm going to combine them to implement arbitrary number of digits. So for the intermediate steps, I need two digits. So if you are a systems person, which some of you are, you know this as the overflow bit in a processor, right? So,
Okay, sorry.
Also one question.
Yep.
Number could have multiple representations.
can it help?
These are single digits.
Yes.
There are double digits. And you have say 2 double digits to have multiple.
No, I am saying that the number 1234 will be represented by this list. Right. So I am canonicalizing this.
Can't have double digits here.
No, I am by definition ruling it out in the same sense as the number 034 and 34 are the same number because it is defined. Right. So I will not allow leading zeros, trailing zeros here, and I will also not allow multiple digits packed into the same element. Right. So this is done so that every number has a unique. So let's so for convenience.
So last question, if you didn't have two-digit numbers, you only had single-digit numbers. When you got that 18, you would have to represent it as a decimal size.
Yes. So this problem is tricky. It will require a lot of if-else kind of handling to check when overflow happens and so on. So if you look at like real world software packages, they do this sometimes, but I don't want to write if else. Right. So I need a procedure make. So Python has, I don't want to keep typing lists. So when I say make n, it should give me the representation of, so let's write some code. And now you have to look at the code. When I make a mistake, inform. Right. So, so I think, oops. So if n is greater than or equal to 10, it has multiple digits now. So I have to append, I have to append the last digit, and then I have to do n is n by 10. Finally, I append n and return access.
Just have it in the right order.
Would it? Okay, let's just test this. Maybe this is better. I think I can do from next star. So if I make 1, 2, 3, 4. Oops.
Oh.
Can you spot the error? Okay, I should use integer division. Yes. Good, good. Okay. Now I think okay, I have to log out and. So the problem here is that Python caches its modules, and I don't know how to. Do you know a way? Okay. I guess we do this. Okay, it looks correct, right? Are you happy with this? Would it work for single digit numbers? Quick. Manoj. Oh, what?
Take the head.
Would it work for single digit?
Greater than 10, right? It will just come out. Can I say it again? Yeah, access append and.
Okay. Okay, let's see. Okay, it works. Would it work for 0? It will, right? Okay. Like 10. Okay. Okay.
Oops. 0 is 0.
No, this is correct. So on the units place you have 0. On the 10. Yes. 0, 5. I think it's not a valid Python number. Maybe 0, 5 is 5. It's a syntax error, but this is not my problem. Okay. So it looks like we have a correct way to convert natural numbers. And this is like a very Pythonic way of doing this, right? So while loop accumulate something into a list, and I think ES112 has many programs that do similar stuff. But notice, now think about how would you prove that this is correct? Harshil. How would you prove that make is correct? Right. So you have to use an induction which you would state in the form of a loop invariant for the while loop, and then argue that okay, if it has a single digit, then it's a fall through and it's always correct. If it has multiple digits, then you apply the loop invariant and so on. Homework. Okay. So I should I mean okay, think will it matter?
Hopefully not.
Okay.
Yeah, I can still see
Uh,
green here, so it's-
Okay, if you are a programmer, you should be defensive and add this. So please always do this
yeah.
in your real programs. Like people should not be able to input negative numbers here because I have not designed for it and I have no idea what will happen. So rule it out. Okay, now let's do addition. So Rohit, what algorithm should we use?
So you're allowing for the two-digit numbers to be atomic entries in the list.
No, I will not put
Oh, you will not
two-digit
put
numbers in the list ever. Right, so it will only hold one-digit numbers. But I can use two-digit numbers in my language, which is like baby Python, let's say. Does baby Python have a name? I don't know. Okay. Okay. So, okay, what is the delay? So the only algorithm here is the grade school algorithm, right? So you move from the units place to the, okay. Now you see that this is kind of complicated. So you have to move from the lowest digits. So I introduce, this is the typical, I think, Pythonic way to do this. So I introduce a variable to move from the places, right? And what should I do? Up to what number should k go? Minimum of both. Okay. So I will need the length of these things, right? So x's and y's are the lists that represent your numbers. So I need to go minimum or maximum.
We have to cover maximum, but go
Okay. Okay. So let's go to the minimum, because when you go up to the minimum, you are guaranteed digits from both the lists, right? And
Then it could have a carry.
yes, we have to handle all the cases. Yes. Right. So okay. And now what should I do? So let's call the output list. So ZS is the sum of x's and y's. You should not do x's plus y's. That is something different in Python. Okay, so go x's of k. Okay, let's see. We have to sum x's of k and ys of k. Right. So you have to detect the carry, right? I cannot now put this in the list. ZS.
Temporarily put it and then see if the list later.
No, I want a single pass algorithm. So that is the sensible way to do addition, right? Okay. Right. So here I can detect the carry. So if s is greater than or equal to 10, then now I need another variable to store the carry and propagate, right? Because the carry has to go to the next iteration. So I say that carry can only be one. And now the real sum is s minus 10 in the current place value or place. Right.
Yeah, it's supposed to.
Right. Good point.
So before while carry should be reached by zero.
Okay, cool. Okay, I should do this more often. Okay, so I have to do this, right? I mean, the corner cases, what if I am at the first digit? I can, without loss of generality, assume that carry is 0 and then propagate the carry at every place.
Maybe next.
Sorry, what?
Maybe next.
No, if I do max, then if xs only has 2 digits and ys has 4 digits, when I try to pick out xs of 2, it will be an error. Right?
But the last carry is not last.
Yes. Okay.
Carry should be.
Carry should be reset to zero.
Consider zero.
Okay, cool. I missed this. So okay, this is interesting, right? So he realized this. So who realized before this? Please show your hands. I did not realize this. Okay, only he realized this, right? So very poor success. Okay, so otherwise we reset the carry because we added the carry and everything. Still, we did not get a 2-digit number. So now there is no carry going to the next digit. Cool. Okay. Now, right here we cannot really do carry. I mean, this would not be enough, right? So you see that. So if I do return ZS here, is that enough? Okay. Leslie got fed up. Right. So, what about this?
The excess digits in the longer list. Need to be put over.
Right. So it is possible that one of these lists is longer, and then we have to like sweep up all the digits and put it. Right. So how will we do this? So we can do while k less than n. So this can only happen if n is the larger or the larger number. And here what should we do? Okay, it's pair programming. Come on. Excess of k. Oh, sorry, I forgot to. Okay, I think Neil told this, but I forgot. So this should be, sorry, ZS of k should be excess of k plus carry.
We can't do this.
Okay, I still cannot do this, right? Because it could again be greater than or equal to 10, right? So I have to stupidly write this. Okay, now we have a carry. I have to do s minus 10. This time we should not forget. Maybe. But okay, it's fine. So what should I do now? ZS of k, sorry, ZS dot append.
You don't want
Yes.
leading zeros with effective.
Okay,
I need n equal to 1.
If carry equals 1.
There is one more case.
So just copy this.
We have to take max of n and n.
right. We cannot take max of an nm because then we will not know which one is longer. So I guess we can do this. So if n greater than m, then okay, right, not then. That's a different language. Okay, maybe WSS XS L if m greater than n. Would this work? Now I can use max and just use the larger list. Okay.
List copies are okay. Because you're not mutating it.
No, this is not a true copy. It's just I will not be mutating x's and y's. So
So the last day only carry is one you should append, right?
At the very end. Z is to depend carry.
Okay.
outside.
So if carry
Not there,
no?
outside.
Oh, okay. But here it should be
It-
okay. And but here I need not have that condition, right?
Yeah.
I'm not sure. See, I don't have a proof and I'm worried about the correctness. So I want to know, how are you thinking about this problem? Like, how are you thinking of the algorithm? So what is the process that is going on inside your brain while you are telling me the code to write? This is the important point, right?
You start writing something simply, and you see that if there's a loop for it, you cover that and then you follow it.
Okay. Yes. It is a part of the process, right? So I am writing some code that I think holds in some general notion, and then you discover corner cases and so on. But other than that, how am I coming up with the general case? Or how are you coming up with the general?
Makes sense that you have a silly visualization in your head with.
Yeah,
point of
you are visualizing these structures, right? So you are visualizing how k is changing, how is carry being propagated and everything. So you have these variables in your mind. So, so people say that you are simulating the machine in your brain, right? So this is what you are doing. This is how you are discovering the algorithm, right? So John Carmack, who was the lead programmer for Doom, which is a very famous game. So he says that our brain is a very faulty interpreter, right? So if you are discovering and coming up with programs like this, you are almost always wrong. This is natural number addition, so you might be getting this correct. But for any program of reasonable complexity, you are almost always wrong. Yep.
We are incrementing K.
Right. So I'm not incrementing K. Right. So this is how systems programmers program, right? So this is how they do it. No, I was a systems programmer at one time. So it's always about thinking about what is going on in the machine and everything, right? So it's never about the higher level things.
You just scroll up to check if you implemented in the other one.
Okay. Okay. I will not ask
I am
any.
leaving before. Now you are going to tell the good stuff, I guess. It was already good, but I am.
Okay, that's not a problem. Not a problem. Okay, so I am incrementing K here and okay.
Thanks.
Does it look fine? So this is again the where? No, I am sweeping up this.
So at first, the K is being implemented. So when the next while loop starts, the K is already.
Yeah, that's okay.
That's when that one you're playing goes to the end.
So I am sweeping up the higher order digits of the next number. Right. So that is not a mistake, but I may be making other mistakes. Right. So this is addition of natural numbers. Hopefully, I have to reset things from that import start. So I can do stuff like 1, 2, 3, 4. Okay, maybe 12. Should not get too ambitious. Okay, I think I have to have an example with a carry. Maybe just 9, 29. Okay. Okay, that has gone horribly wrong. So what is the mistake? It is correct. Oh, okay, yeah. Oh, I am getting confused by my representation. Yes, right. So let's see a more right. So notice this is also something that you do, right? So you try to invent the corner test cases and see whether you have sufficient confidence. So let's try 0. This is a corner case. It's okay. Okay, well, tell me more interesting cases. 99, is that interesting? Okay. Okay, okay, just tell me the addition.
88,
12 and 88. Okay. It should be 100. Okay. Okay. So now you are kind of confident that, okay, this works until you see the next mistake, right? So also this is like a very typical way to debug Python programs. You try and invent corner cases. So this is also called white box testing, right? So why is it white box testing? Right. So we know what is in the box. We know the algorithm. So we know the corner cases and we are like trying to break the algorithm, right? And your confidence increases as you see more and more positive examples. So this is like a very scientific process, as in like a natural science driven process, right? It can be falsified anytime, right? So no matter how much I test, I cannot be absolutely sure because there are infinitely many natural numbers. Now, homework, write a proof that this is correct. Right? So again, you have to write a loop invariant for this thing, a loop invariant for the bottom thing. Now you see it is much more complicated than make. Right? And I bet the proof will be longer than the algorithm.
There are more steps in writing this book.
I can factor this part probably out into a. I'm not sure about this. Yeah, you can. Because ys of k is 0 always in the bottom part, and that's it. So it can be made more succinct. But the complexity of your proof, I think, does not go away. You still have to do both loop invariants. So where have you seen this structure before? Merge sort, yes. So we are doing a similar thing, right? So we are traversing two lists in parallel, and after this, sweeping things up. Good. So you're familiar with how you think, and I'm going to say that this is correct. I'm not sure, but move on. At least it worked on all the examples that we have tried. Are you like how many here are confident that the code we have written is completely correct? Okay, 50% strike rate. Okay, not even 50% are confident, which is typical. So it's fine. There are these annoying bugs, right? So I think last year during DSA, I was writing like a program. It worked perfectly like during the demo, and then after the lecture, some students compiled and ran and said that okay, this is not working. It was a program to play tic-tac-toe. So I could not try all the possibilities of playing tic-tac-toe, but on some choices of positions, the algorithm made a mistake, right? And it was kind of subtle. And the program was way too big for me to write a complete proof, right? So it's a very intractable problem. So the way people solve this is by writing a lot of tests. So for most of the like real world programs, the test code is actually bigger than the actual code, right? So okay, so Python is boring. So let's switch to OCaml. Okay, some package is missing. I hope that's not a problem. Okay, so now we are going to use a different language, and I'm going to demonstrate a significantly different approach. So the funny thing is, whatever approach I'm going to be using is possible to do in Python, but I bet almost all of you never thought about this, right? So when I said you have 2-digit integers and you have all the other Python things, this is the only representation that came to your mind, right? So does anybody have a different way of doing stuff? Significantly different, like not pack 2 digits and do some variable like that. That is not useful. No, right? Okay, I'm intimidating them to say. Okay, so okay, so what is the definition of a natural number? You.
Numbers which are greater than 0. And so if you like this, rational numbers are denominator as well.
Oh no, no. We will not define natural numbers by denominator one. Okay, so this I will just state this.
This can be found.
Right. So I find that almost everybody struggles this question because natural numbers are natural numbers. What is there to define? Right. So the mathematical definition is 0 is a natural number. If n is a natural number, then there is a natural number called successor of n, and these are all the natural numbers. Okay? So this is the inductive definition of natural numbers. So this is OCaml. So I can define the type nat, which I will use to stand for natural numbers, and I can say that okay, a natural number is either 0 or a successor of nat. Right? So this is a type definition, like a struct definition or a class definition in Python. Right? So I'm saying that there is a type nat, and you can construct values of type nat as a 0 or a successor of nat. Right? So if I type 0 now,
This one 0 is a constant? Or
yes, 0 is a constant, and successor is kind of like a function. So it's something called a constructor. Right? So functions are applied, constructors are not applied. So you will see. So if I type 0, then it tells me that, okay, 0 is a natural number, and you just typed this. So I can give it names, right? So I can say that let A is 0, and I create a variable A which has type natural, it's 0. Now I can say that B is a successor of A, and notice that it says, okay, B is a natural number and it is successor of 0. And I can go on and I say that, okay,
B is what we think of as one.
right. So B is what we think of as 1, exactly. So now I can create C, and it says, okay, C is a natural number, it is the successor of 0, right? So how would you represent 100? So successor. So if I build 100 here and I print it out, it will take a lot of how much space? 100 units of successor and a 0. Not good, right? So what is the problem?
I think if you want to deal with n, you have to manually apply successor n times is what it looks like.
No, that is not the problem. So the problem is I stated
Oh, storage.
n should only take log n storage, right? So this is a completely unreasonable representation. This is the correct mathematical definition, not in TCS, right? So
But that's only because it seems to be expanding not free. Like,
okay, right. So recall this type definition. What it says is there are two ways. So this OR bar is so this represents a choice, right? And there are only two ways to construct a natural number. Either you write 0 or you have to write successor of a natural number. So you can prove that the only way to represent 100 reasonably is by doing 100 times successor, right? So
in terms of storage, you're saying that it's also.
yes,
Because it's literally writing out successor.
yes. So notice that I said this is not a function. If it were a function, successor of 0 would have been something, and then successor function would have been applied. But a constructor just is. So it's like a tag, right? So if I write now let D is
Wondering why it didn't say successor of B.
okay. No, it prints out the value and B is name for another. It could have, but underlying representation will be this expanded out thing, right? This is linearly growing, which is completely unreasonable. So many classes would show this. This is basically the unary representation, right? So how can I fix this? So there is a simple way to fix this. I can write natural number is a 0 or a successor of a natural number, or it is twice of a natural number. It accepts this definition too. Now I have three different ways to construct. You can construct 0, or you can say that it's a successor of something, or you can say twice of something. This is much better, right? So how would you represent 100 in this?
Twice of 50.
Right, it is twice of 50, which is twice of, so if I say it is twice, so now it should be 25, which should be a successor of 24, which is twice of,
Twice of 6.
okay.
Maybe 100.
Okay, this is fine, right? So I'm trying to write 100, it should be twice of 50, it should be twice of 25, should be successor of 24, twice of 12, twice of 6, 6 is
Twice of successor of
twice of successor of
2.
twice of
Successor of
0. Good.
twice.
So if I print out this number, it will just reply, right? So it is not a function because it is not being applied. It just is, right? And how much space would this representation take? It is log n, right? Because at every other step, the number will definitely halve, right? So it gives you the recurrence relation. Storage of n is less than or equal to storage of n by 2 plus 2 or something, right?
This is binary.
Yes, this is just by kind of binary. It basically partitions natural numbers into odd, even, and zero. That's all it's doing. All right. So we have a problem here. So the earlier representation had this interesting property that every number had a unique representation. Now we do not have the unique. So why did you write this? And right. So whatever you came up with is the canonical way to, whenever you have an even number, you do twice and then go to the recursively do the representation of the by two thing. Right. So this is okay. So
It's unique if we agree on this specific.
right. So it's unique if I agree on the procedure, right? So I can write 2 as successor of 0, and I can also write 2 as twice of successor of 0, which is the correct representation. So they both have the same size. Which should I choose? Twice of successor of 0, right? Because every even number I should apply twice. Right? So that is the nice way to define it. It's so if you have good mathematical taste, this is what you should use. Okay, so now let's try and do some OCaml. So we define 0, successor of net. By the way, OCaml does not have unbounded natural numbers. So we are okay. So that was first line is the same as whatever we did. Now let's write the make function that we wrote in Python. So how would you make this? Okay, if you don't know OCaml, it is
Apply the algorithm that you just
yes. So we are just going to apply the algorithm that we described. So maybe n mode 2 equal to 0, then twice of make. Okay, what is integer division? Let me check. Okay. Make yeah, n by 2 else right. So I think I have to do some base cases. If n is 0, then 0. Okay, I think this. Okay, I will come to this question. Sorry, this should be int.
I think that'll get observed in the model.
Right. So else you do successor of make n minus 1. Okay, and this should be fine. Let's. Yes, it automatically returns. There is no. So if I do make 100, I should get back. Yeah, sure. So I get back this. I will take like 10-15 minutes. It is actually much easier to write a program here. Right. So is this correct? Can anybody verify? Should be correct, right? So now notice that if you look at this make, you are kind of more confident that this is correct. Right? Even if, are you? I'm not sure.
Right.
Okay.
Binary.
Right. So
Not exactly binary.
it is not exactly binary. I think it takes maybe more space. It is not a place value system. It is the storage requirement is asymptotically the same as binary, but it's not a place value system. Right?
Like usually binary because the number is being given as the sum of powers of 2, but if you look at what happened with 100, you're writing it as 50 plus, so it's already not, the components are not.
Yeah, it's not the same, right? So, okay, so let's assume make is done. So now we okay. So now we want to add two natural numbers. Okay. So I skipped the n greater than or equal to 0 check there, but yeah, it can be done. I don't want to. Right. So how would you write the add function? What can nat be? So notice that n and m, they are natural numbers, which is the type that we defined, and every natural number has to be one of these things. Right? So we get something called pattern matching on data types. So I can write that match n comma m with right. Let's say if n is k and m is 0, or if n is 0 and m is k, then what should be the sum? K, right? That is trivial. So this language construct is called pattern matching. I think it is present in Python now. I mean, it is present in Python now. So basically, we are destructuring the data, right? And notice that we use the capital letter for the constructors and are using small letters for the variables. So this is how OCaml distinguishes. When it says a capital letter, it recognizes that it's a constructor. So this k will be matched with any number because it's a small letter. And this 0 will only be matched with m if m is actually 0, the number 0, the nat 0. Okay. Now, the other cases. So if it is k comma successor of 0 or successor of 0 comma k, then we have to increment k by 1. Right? So this is a bit tricky. So I will write successor of k and I will write. So why is this tricky? So if I write, is this correct? No, k is just a natural number. Right? So what this clause is saying is that n and n is some number k and m is successor of 0. Right? And this is saying that n is successor of 0 and m is some number k. In that case, the result is successor of k.
Because line plus 1 is when.
Yeah. Yes. So 9 plus 1 should be 10. So the first constructor or the outermost constructor should be at twice. Right? So what we will need is we will need a function to handle this. So I will just write successor of k and let's write this one. So if it is 0, what should be the successor? If it is twice of k, I can write successor of twice. Right? So if the number is an even number, then to increment it by 1, I can just apply the successor constructor. Right? What if the number is successor of k? Now, notice that I cannot really write anything here because if the number is of the form 2n plus 1, so I will write it in more familiar notation. So if the number is 2n plus 1, then I cannot write 2n plus 1 plus 1. Right? So, but what is 2n plus 1 plus 1?
Twice of n plus
Right. So it is twice of n plus 1. Right? And right? What do we know? So if successor, if the number is a successor of k, what can we say about k? No. No. What can we say about k? This is just one. So if we see successor of k, then we know that k must be even, right? Because we apply the successor construction only if the inner number is an even number, right? On the other, like in other words, there cannot be two successor constructors back to back, right? So I can say that this will always be twice of k for some k. So now what should be the result? What is the successor of twice of k?
Twice of successor.
Right. So it is twice of successor of k, right? Where this is the recursive call. So here it's not a recursive call. I'm just calling the constructor. The small s indicates that it's a recursive call, right? So what is the running time of this function, this successor? So notice that all the first three clauses are constant time. The last one is
Takes you down to the-
yeah, it takes you down recursively to half the number, right? So the recurrence is
log.
t of n by 2 plus 1, which is log n, right? So I will just write this fact here. So in fact, successor is constant time for even n and log n time for odd n, right? It's constant time because here it's just constructor application, right? So it's not a recursive call to the function. Okay, so now if I say, okay, so notice that when I added this, OCaml complained with a warning, right? And how much time do I have?
Then I will.
Okay, so if you are not enjoying this talk, you should leave. I will not punish you. Right. So OCaml is complaining that this pattern match is exhaustive. That is, there are some cases that I miss. Right. So what are the cases that I missed? Here is an example of a case that is not matched. Successor of something or successor of something.
Those are cases that you said wanted.
Yeah, those are cases that we know will not happen, but OCaml does not know. Because what we have told OCaml is a natural number is a successor of a natural number. And a natural number can be a successor of a natural number, therefore. So this is an invariant that we have that she does not know about. Right? Okay. So we can avoid this complaint.
Can you do a dummy match?
Yes. So I will do a dummy match. Exactly. So I will say that if the number is successor of 0 here, then I will say, so there is a primitive fail with invalid number. But I know that this will never happen if we have programmed everything correctly. So this just
To avoid the comparison.
yeah, this is I think the complaint was also from here. So let me test this again. Right. Okay. So notice that now it has stopped complaining for successor because now it knows that I have handled all the cases. This is a really cool feature, right? It does not let me miss cases, right? Whereas recall that in the other thing, you had to run the program in your brain to find the missing cases, right?
So, right, if you ask how does the compiler do this, is that like when?
Right. So how does the compiler do this?
That like go and take a compiler's course or no?
No, because I told that all natural numbers will be of one of these three forms. So I have beforehand told it that these are the only three cases. Now, whenever I handle natural numbers, you make sure that I handle all three cases.
But it's
Okay, so now,
Last later.
no, it's a good question, right? So when OCaml sees I am matching a natural number, it knows that I should be handling successor twice and zero. So it says, okay, he is handling zero. He is handling successor, but this pattern is not arbitrary. So it's only handling successor of zero. Twice case any even number. So I am handling all the twice cases. But I am not handling things like, so at this point it thinks, okay, maybe successor of twice of something. It's not handling. But here I handle successor of twice of something. Right? Now only the remaining case is successor of something, which is what it complained about. So when it says successor of whatever, it has now concluded that I am actually handling all the cases. Right? So this is
we just
basically,
look at the three lines that start with a successor, you see zero twice and successor, so that's all.
yeah, exactly. Right. So in the second position, I am handling all the three cases. And this pattern is also arbitrary. So that also.
Yes, I was wondering, in general, the fact that it can do like.
Yes, it can recursively go in and check that all the subcases are being handled correctly, right? So this is like so if you do proof by cases, you know that this is very frustrating, that if you have too many cases, you have to ensure that these things are exhaustive. So here the compiler does it for us, which is not surprising because OCaml was originally designed to for interactive theorem provers. So this is one of the key features. If you miss case, it has to complain. Right? Otherwise, your proofs are wrong and the compiler is happy, which is a bad situation. Okay, so let's get back to addition. Okay, let's do the easy cases first, as is tradition. So if the number is, in fact, I don't have to invent new variable names, right? So I can just rebind m. So this is a new n and m, right? It recursively matches the inside. So if it is twice n or twice m, what will I do? What is 2n plus 2m? Right, exactly. So it is twice. Okay, I will write twice, add n m. I should write the twice function. So this function is simpler. There is only one. So I cannot blindly apply twice constructor because then twice of zero will be twice of zero, but twice of zero should be zero. Right? Okay. That OCaml cannot help with. Here it is twice of. So this is a constant time function, right? So this is not a recursive function. I did not write rec here, right? So to denote a recursion, just an application. So if it's zero, you have to go to zero. Otherwise, you can always apply twice. Does not matter what the inner constructor is, right? So, okay. What about what is the other easy case? Two odd numbers. So successor of n. Okay. Let's see. So if I write this, I am in trouble. So now I have to write successor of n plus m, but I don't want to write this. Right. So because now I do not have t of n is t of n by 2. Right. N and m are only one smaller. So what would I do? Right. So what do we know about n and m here? What do we know about this n? What can this be? It will always be even. So I can write twice of n to match everything here. And I can write twice of m to match everything here. Now what should I write here?
Twice of add and successor.
Okay, right. So I can write this, but this is also not good. We will fix this later. Why is this not good? Okay, you can think about this. Let us do the other cases. is it does not correspond to T of n is T of n by 2 plus constant. Okay, what is this case? Twice n plus successor of twice m. What is 2n plus 2m plus 1?
Twice of added.
Right. So successor of twice of add nm. Okay, what are the other cases? Okay, why am I asking you this? We know. Okay, successor of twice, successor of successor. Okay, the complementary case. Successor of twice, twice of m should be what? Okay, I think I should have combined these, right? Okay.
Then again, something about the successor.
Sorry, what?
This is successor twice,
Mhm.
then successor, the comparative.
Yes. Because it does not know, right? What? I'm still missing this case, successor of twice.
Successor. Back-to-back successor.
Back-to-back successors.
The second.
Right. So I have to add this case to make it shut up. So if the first pattern is this, or the second pattern is this, then I know that we have to. I mean, this is the case that will never happen, right? If you are properly handling stuff. So if it fails here, we know that some problem has occurred. Then you debug. Like some debugging is avoidable. Cool. Right. So stare at this code, make sure that it is correct. And I claim you can convince yourself of this much easier than the Python version. Is everything correct?
It doesn't seem a little less overwhelming. Like, double.
Yes. So basically I'm just writing a bunch of equations, right? So if one of the numbers is 0, then it's just k. One of the numbers is 1, then you just take the previous successor. Both are even, then you add the smallers and take twice. Right. So these two cases are basically the same. I should have combined them. Odd and even, you get 2 times n plus m plus 1. And two odd numbers, you get 2 of n plus m plus 1. And okay, I will give some exercise. Unfortunately, there is a bit more to be said here. Right? So, but I hope that you can see that it's correct, obviously. Like I am way more confident of this being correct than the other one being correct. And you should also be. Right? Because it's just equations. Right? And this is so why were we able to do this? And notice that you did not know OCaml, yet you are more confident. It has nothing to do with OCaml. Actually, I could have written the same program in Python.
And you can also do lists in OCaml, I guess.
Yeah, you can do lists in OCaml, but I would never write this in OCaml using lists or in anybody's name. So, but why didn't you write this program in Python? You can write this, right? So you can create a number class, then 3 classes, 0, successor, and twice, which inherits from the number class. So this is a closed inheritance hierarchy, and then you can do match. I think everybody knows about this.
Yeah, I don't know if I don't know if I would realize that matching can be done in this way, but I don't think that's the key. You can also do this with if else, I guess. Match is completely different.
Yeah. Right. So you can do this if else, but I mean you will still need pluses because I
Right,
only
you
give
need
you 2-digit numbers. Right. So why didn't you think of this in Python? Well, that is my key point. Right. So why?
We started with the list representation.
Right. So why did you use lists? This is also a list, right? So did you notice this is also a list? So what is a list? A list is either empty or it is the first element followed by the rest of the elements. It is either 0 or it is 1 followed by something else. So they are completely isomorphic.
It's an assumption of those 9 digits in the C++, in the Python. That we don't-
No, you could have still written this code with that assumption. I mean, here I'm not actually assuming anything. I am not even assuming that there are integers in the language.
But we need list.
Right. So exactly. So Python has this philosophy that, or it was built with this philosophy, right? So we will give people lists. Sorry, we will give people numbers, strings, floats, lists, and dictionaries, and this is all they need. This is the defining philosophy. Right. So everything, and it is not actually Python's philosophy, right? So there is,
classes, I guess, no?
I think it came a bit later. Right. So this is also the defining philosophy of Lisp, right? Which is short for list processing. And the defining philosophy of the language is everything can be represented by lists, even code. So you don't need anything else, right? So the philosophy behind Python is we will provide a bunch of really powerful data structures and people will be able to build anything they want by combining them. Right? So this is what you do. I mean, maybe you are not completely conscious of it, but this is what you do, and so you naturally gravitate towards, okay, let's represent it as a list of numbers. So the competing philosophy here is, so what is the philosophy here? So here it makes type definitions easy. Okay? So the philosophy here is that, okay, people will want a bunch of different things. So we make defining the shape of data very easy. So I could define NAT as 3 things. It has to be one of these. You can do it in Python in like 20 lines, which is why nobody does this, right? So there is the principle of least effort. So given a task, you will try to solve it with the minimum amount of effort, which is exactly what you did. So it was completely logical in both cases. Right? I mean, you don't know OCaml, but if you knew, this is the first thing that you would jump to because it takes one line. Okay, why don't I do this? And notice that again, the code is smaller. It is easier to keep in your brain. It is easier to like reason about.
Is that why you said you'd never do it with lists and vocabulary? Because lists, in terms of ease of implementation, would be better with Python.
Yes, it would be totally comparable to Python, but it is not the most painless way to do it in OCaml, right? So you will always choose the most painless solution that is available to you.
Least painful.
Yes, which is okay, least painful, which is what I mean when I say that the features provided by your language shapes your thinking, right? So okay, this code is actually not complete. So what is the issue here? I want, so there is no issue here. It's actually still linear time. But if you look at this case, so this is T of n by 2. Both these numbers n and m are like half the size of the original numbers, but I am applying the successor function here. And I don't know that n plus m will be an even number, right? So this could be an odd number and this could now take log n time. So if you argue like this, what you get is this is T of n is equal to T of n by 2 plus log n. I mean, it actually does not happen. So you can, so the only issue I have with this is the code is clean, but the proof is tricky. and this is not a situation you want to be in, right?
So you're saying the cost of a few more cases or whatever? you
Yes.
want to-
So you can.
So-
Oops. Okay. So you want the code to be simple and easily understandable, right? And you can refactor this. So how can you refactor this? So this is unfortunately I will leave this as exercise, but it's a good opportunity to like try and write something in OCaml, right? So I would.
You can put this up in the gist and share the link.
Yes, I will share both Python version and this. Okay, so again, in functional languages, this is a very common thing to do, and it structures your thinking, right? So I know that successor of add of nm is bad, right? So I define a new function add1 nm, and it should be computing n plus m plus 1, right? And that it should do in linear time. If I can write that add1 function, then I am done. Right now, write the add1 function. So you can do this in log n time. Right now, what is the advantage? So this add1 nm can call add, right, recursively, and you already know that add solves in log n. So I will also put up the complete solution next week. So you get 1 week to solve it. Uh, and please do share the solution. So you can write. Okay, if you want, I will just structure this. So you can write. I will have a dummy implementation here, which you can try and fill in, right? So this one should be. I mean, it should not be this, but it should have the same behavior. And now you should argue that it is log of linear time, right? So that is all. Fill in that add1 function and then you will be done. Again, it is the same thing, right? So the beauty here is that I have defined n and m as 3 clauses. So the only thing you can do with n and m is pattern match on those 3 things. There is nothing else you can do with natural numbers, right? So in a sense, this restriction is very liberating, right? Because the compiler can help you when you miss cases, and there is, so by channeling your thoughts into like a very narrow focus, you reduce your problem space. Whereas Python gives you like a very general structure. You have a list of numbers. What if one of my algorithms puts a negative number in my list? I will never know, because Python does not know that my list should never have a 2-digit number, or because it has no way of knowing. I did not define it for it, right? But here such issues will not happen. Clear? Okay. So I will share this. Thanks for coming. Yeah, so if you have been in my lectures, you know that I overflow time by a lot always. So, okay. So any questions? Please do share if you sorry. Like you need not install an OCaml compiler. I think you get the idea. So you can just try writing add1 on paper. It's a good exercise. You should always start by writing programs on paper. Okay, I should not say that. It depends on your mode of thinking. So I am very comfortable with solving things out on paper.
And share it on online OCaml reference.
There are, but I almost never use them. I think there are online OCaml records.
If you can try OCaml without it.
Yes. So I think if you, I think even the official website has an OCaml record online. So should be. Okay.
I guess if there are no questions, let's. If you have a pack of playing cards, give me a moment to finish.
Okay.
Great, thank you. Lovely. Any other how strategies with the people dynamics related to
These two? Okay, what is that?
Oh, it will be because I feel that it would be
Okay, I should give it to them.
yeah, yeah. People who wonder should stay back for a minute.
Please stay back for 5 minutes.
So then you need to the difference.
Just just initials, not
Oh,
sign.
whatever, yeah. You can also add it.
What?
So
How many?
those of you who are connecting, mind for everyone. For those of you who are come to your CSE Seminar Series, if you select another thing to get a game or a book at the end of the so please keep coming back to CSE Seminar. Alright, thanks so much. Thanks for coming. All right, thanks for doing this. It was amazing.
No problem. Enjoyed. Okay, can I stop sharing?
Yes, I think you can.
Cool. Okay, so if anybody is there online, thank you for joining. If you have any questions, you can ask one.
So I think Aditi was online and a couple of people were online, but I think they've dropped off by now. So
Okay,
I think they probably realized at the top of it. So right now it's just us.
okay.